Today we're going to learn about support vector machines. First, let's go over the basic principle of classification. Let's say we're trying to classify objects as a boat or a house. All objects before the coastline are boats, and all objects after the coastline are houses. The coastline serves as a decision surface that separates the two classes here. New objects are classified as boats if they fall below the decision surface, and as houses if they fall above it. What is SVM? It's a supervised machine learning algorithm that involves classification. The steps are to plot each data item as a point in ND space, where n equals a number of features available. Then we find the optimal hyperplane separating the two classes, and we perform classification. Let's look at one scenario. A and C don't separate these classes very well. B does separate them. Here we have a series of lines, all which separate these two classes. But we want to maximize the distance between the nearest data point of each class, which is called the margin. C has a higher margin compared to A and B, so A and B have a higher chance of misclassification. How does SVM work? The circle and triangle are the two classes we're trying to classify. Here we have a margin. The margin is the distance between two hyperplanes. In SVM, we want to maximize this margin. It's not maximized yet. Now the margin is somewhat bigger. We keep increasing the margin until it's at its maximum. When the margin is at a maximum, we have the optimum plane that separates these two classes. Let's do some math. The equation w dot x plus b equals 0 is actually an equation of a straight line where w is the slope of the line. These two lines support the optimal plane, and so they're called support vectors, hence support vector machine. D is the distance between support vectors, which is actually the margin. In SVM, we need to maximize the margin, so equivalently, we need to minimize 1/2 of absolute value w vector squared. To make it simple, let's say we have a new example. We don't know what it is. We know that it is either a triangle or a circle. Now we feed our example to the equation f of x equals sine of w dot x plus b to find out what this object is. Here x in the equation is a triangle if f of x is negative, and if f of x is positive, it would be a circle. Let's go over linear separability. If two groups can be easily separated using at least one line in the plane, they are called linearly separable. In our previous example, the red circles and blue triangles are linearly separable, as a line can separate them into two. But two groups are not always linearly separable. Here we have an outlier. We cannot separate these two classes using a straight line. If we ignore the outlier, we can use a hyperplane to separate them. Here, we don't have any linear hyperplane. We could introduce a new feature. Instead of adding a new feature, SVM has something called a kernel trick. The kernel trick takes low-dimensional input space and converts it to higher dimensional space. It takes a non-separable problem and makes it into a separable one. Here we're trying to separate tumors and normal cells. It's not linearly separable. Using the kernel, though, we can separate it into two separable classes. Let's go over some key SVM parameters that we'll see in the coding exercises we're going to perform. For the kernel, we have linear, RBF, and poly. For gamma, we have kernel coefficients for these. The higher the gamma, the more we're trying to fit it to the training set. A gamma that's too high could cause overfitting. C controls the trade-off between decision boundary and classifying the training points correctly. Now that we've gone over the basics of SVM, some basic parameters, we're going to try out some coding exercises so we can see it in action in Python.